All right, welcome everyone. Welcome to real-time streaming scenarios on HDInsight. My name is Raghav Mohan. I'm a program manager on Azure Big Data, and I focus on streaming scenarios on HDInsight. So you're hopefully sitting in the audience here today because you want to deploy a real-time streaming pipeline for your enterprise use case. You might have heard of open source technologies such as Kafka, Storm, or Spark Streaming, and you want to leverage these technologies for your production pipeline. The challenge with getting up and running with big data streaming is that getting it correct for enterprise production use cases is hard. Getting it correct with open source technologies is even harder. I will show you today how HDInsight abstracts away a lot of this pain so you can get up and running for your enterprise use case within minutes. The big data streaming space is increasingly complex. There are new technologies that are emerging every day, such as Kafka, Storm, Azure Stream Analytics, Event Hubs, Spark Streaming. We're going to go ahead and understand what it means to architect a big data streaming pipeline, what the necessary components are, and where each of these technologies fit in, so that you are better equipped to make the trade-offs between these technologies when you have to architect your big data pipeline. Next, we will build a real-time streaming pipeline using HDInsight today for an IoT scenario, and we'll understand the enterprise features that HDInsight has to offer so that you can leverage them for your business use case. Then finally, we'll understand some of the customer journeys on HDInsight. We'll leverage the learnings from our customers that have deployed their streaming pipelines so that you are better equipped to deploy it when you have to architect it for your use case. So why might anyone want to build a big data streaming scenario? As this slide shows, streaming opens up a whole vast use cases, and we won't go into every single use case because that will be a whole session in itself. But if I were to just pick one so that we can put some context into the streaming scenario, we can pick anomaly detection. So we have a lot of customers that do point of sale transactions, and they have data that is streaming in for point of sale transactions. They want to analyze which of these transactions are fraudulent transactions so that if they can analyze this in real time, then they have a window of time when they can act on this information to prevent further harm from happening. You can also imagine that this can be applied to a financial advisory firm where there's data coming in from each stock trade that happens, and this might be millions of transactions per second. And you want to understand which of these transactions are related to maybe insider trading so you can flag them. So you might pull together data from other sources, in real time run some machine learning to understand that. Real-time streaming also opens up a vast majority of IoT scenarios. The new buzzwords in the industry are connected buildings, connected car platforms. If you were to pick on the connected car platform, imagine you're running a fleet management system and your fleet has grocery trucks involved. You want to pull together real-time weather data to understand do your trucks have the correct temperature inside so that when they arrive to their destination, do you need to make some modifications to the temperature sensors for your trucks? If you also were to pick on the connected car scenario for personalized recommendations, each of your connected car sensors have some data that's going to flow back to the system. So for example, you might have some brake sensor data that is flowing back to your big data streaming system. And if it falls under a certain threshold, you want to alert the user to say, hey, your brakes are about to need servicing. You might want to take it into the shop. However, let's say we have user profile data. So in that scenario, if the user speeds a lot, they probably brake a lot. So if it falls below a certain threshold, you might want to alert this user faster than other users so you can offer these sort of personalized recommendations in the connected car scenario. So how might we go about architecting a IoT or a connected car scenario? We have a lot of devices that might be deployed out in the field, and they're sending data back out to a lot of their sensors. This data will flow into something as some gateway. This can either be an IoT hub or a gateway that you have deployed on your own. Once this data flows into the IoT hubs, we'll then pipe the data through into some sort of stream processing engine. And this is going to be more of the focus of our session today. And this stream processing engine can either be Azure Stream Analytics or open source technologies such as Kafka, Storm, or Spark Streaming. Once we run some sort of stream processing analysis on here, then we can either pipe this data out to some sort of archived storage. This can either be your Azure Data Lake Store, your Document DB, or your HBase, or you can kick it off to some other process that's going to take this data and then do some more processing on it, maybe report it back to the application to alert the end user, or you can report it out for your monitoring and your real-time dashboard views. So while talking about big data, connected car scenarios and their architectures is great, wouldn't it be better if we could actually build one in minutes here today? Who would like to see that? Everyone? OK. So let's start with the connected car. And I asked my manager if I could have a connected car out here on stage for this demo. And he did not give me enough approval or budget to do so. However, he did give me approval for a toy car and an Arduino Uno board. So what I have here is a toy car and an Arduino Uno board. And this is going to send data via Bluetooth to my laptop, which is going to act as a gateway. And from my laptop, I'm going to send data to Azure HDInsight, which is running a Kafka instance. And that is going to send data back to a real-time dashboard, which we'll see. And for this demo, I have programmed an accelerometer, so we'll see a dashboard go through. So let's see this in action. This is our speedometer that's going to send data back. And as we can see, the data is streaming in over Bluetooth onto my laptop, and it's sending the information back to my Kafka instance. And I need to turn the car on. Let me just refresh this page. So as I go up and forth on the stage, you can see how the dial moves back and forth. And this is, again, data not coming straight from the car to my laptop. It is going from the car to the gateway, which is my laptop, all the way to Kafka and back. And we'll look into Kafka as a technology, but it is a technology that's built to handle trillions of events per second. So if you do see a lag in delay, it is because my laptop cannot handle the load of Kafka, and I've put in a millisecond timeout here. So we'll go back, we'll revisit this demo to understand how might we architect this after we've deployed the HDInsight technologies. But switching back to our presentation, hopefully this demo got you a little bit excited about how easy it is to set up a big data pipeline for a connected car scenario and use for your production use case. So let's talk about building a big data streaming pipeline. But before we can talk about how we would architect a streaming pipeline, to provide some context, let's talk about where a streaming pipeline would fit into your big data architecture. So to build a robust big data architecture, traditionally there are three components involved. You need some sort of component where you're going to land your data. This is going to be your ingest data. This can be data that streams in maybe every 4 hours from web traffic logs or some databases. Or it can be event data that we just saw right now streaming in. Once you've landed this data in, you need to have some sort of data processing layer where you're going to clean your data, maybe run some ETL on it, run some transformations, do some machine learning, draw some insights out from this data. And then, once we have drawn these insights out, we're maybe going to land this data out to some presentation layer. This can be either your SQL DB instance or SQL DW instance that's going to then provide a end presentation for your users, which can either be a Power BI dashboard, it can be another application, or it can just be another store where you might pipe the data through. So traditionally, this whole pipeline would come and complete within hours to maybe even a day. And that used to be OK. But as we just discussed for the real-time streaming scenarios, we want some predictive analytics. We want some real-time machine learning. So very, very smart people back in the day decided that we're going to chop this data pipeline up into 2 layers, known as the speed layer and the batch layer. So while we still have those batch computations that go run at night, that do hours to maybe even day computation, they do really extensive computation, we don't want to lose those computations, but we also want real-time insights. So what the batch layer is going to do is it's going to run the jobs, and it's going to store the results of those jobs in something known as batch views. They're essentially just checkpoints of the results that it stored. As the data streams in during the stream layer, it can just view the last checkpoint of the batch view and join that in real time and give you back the results. Then in the next iteration of the batch layer, it will take the results of the streaming pipeline and then compute that into the next batch. So in this case, we have both the benefits of the speed layer and the batch layer without having to compromise on either the functionality or the speed. This is famously known as the Lambda architecture. And the reason why it's called Lambda is because Lambda splits into two, and they split speed and batch layer into one. For the focuses of this talk, we're going to focus on the speed layer, because that is where the streaming pipeline will live. But I encourage you to check out, there was a talk yesterday on architecting big data robust solutions, where it really walks through where each of the Azure technologies fit into this big data pipeline. So if I were to zoom into this speed layer, let's talk about how we would go about architecting a streaming pipeline. So similar concepts for event ingestion and event processing apply for streaming pipelines. We have data that's flowing in from your business applications, from your sensors for your cars, or even custom applications such as your web traffic, the click-through events that are streaming in at a very, very high rate. We need some place to land this data. Now, if we look at in the connected car scenario, we have about 1,000 to 2,000 sensors deployed on each car. This can be about hundreds to about 1,000 cars deployed within each square mile radius. That translates to about millions of events per second. And as we sort of scale this out to multiple regions, that number grows tremendously. So we need some sort of technology that is specialized in buffering these events, that is going to say that, yes, I'm going to get your events, and I'm going to act that I got them, and just store them in this ROM format. So on Azure, we really have two technologies that enable this to happen. There's Azure Event Hubs, and there's Apache Kafka that is powered by Azure HDInsight. Once we've landed that into our event, and we'll go through what the differences are between these two and the trade-offs. But once we've landed them into our event buffering component, we're going to then run some sort of stream processing on this. Now, this can be either you want to get the data out from your buffers, or it can be some transformation. You want to turn them into Avro for columnar format, or you want to do some real-time machine learning and then report that back out to either your dashboards or just land the results back into Store. And we will discuss the trade-offs between Stream Analytics, Storm, and Spark Streaming in this presentation as well. But before we can discuss these trade-offs, let's go through some of the streaming concepts just so that we can understand what are the necessary components that we need to evaluate our streaming technologies against. So when we talk about streaming data, we really talk about data that is in motion. This is continuous data that is flowing in at every single second or a millisecond. And we need to review a couple of semantics. The first one we're going to review are windowing semantics, and the second one is stream processing semantics. Let's start with the windowing semantics. We need to have some construct that is going to say when data is streaming in continuously, how do we think about analyzing this data, and how do we think about analyzing data for a certain window of time? So we're going to have two concepts known as a slide interval and a window size. The window size tells us every time when I evaluate my streaming pipeline, how many seconds of data am I going to look at? And the slide interval is going to say, how often am I going to execute this evaluation? So let's walk through an example to understand how this works. So let's say our window size is 10 seconds and our slide interval is 5 seconds. So at times t equals 10, let's say that 5 events came in from 0 to 10 seconds. When we evaluate our window at times t equals 10, these 5 events are just going to flow through. However, our next slide interval is going to be 5 seconds later. So now we're going to evaluate our window again at times t equals 15. But let's say that no events came in between 10 to 15. So now our window will look back 10 seconds. So window will contain everything from times 15 to 5, and we just get back 462. Similarly, if we have 2 more events that flow in from 15 to 20, then our window contains 10 seconds worth of data. In this case, it'll go back 20 to 10, and we'll just get back two results. And as you can see, this can just flow on from here. But what might be a business use case for why we might want to use a sliding window? Let's say that I want to answer this query. Every 5 seconds, give me the count of tweets over the last 10 seconds. So in this case, in this example, we didn't actually do a count. We're just outputting the data as it comes. But when we do evaluate our window, you might imagine, you might imagine that you might want to do a count here. So instead of outputting out all the events, we'll output out 5 for the first window, 3 for the second window, 2 for the third, and so forth and so on. If we extend this concept, we get the second sort of windows, which are the tumbling windows. To think about this, the most simple way to think about this that helps me is there's no overlap between the windows. So in this case, our slide interval and our window size is the same. So if you evaluate our streaming pipeline at, say, times t equals to 10, then 5 events come in, our window is 10 seconds. The next evaluation that we will have occur will be at times t equal to 20 because our window, our slide interval is 10 and our window is 10. So we'll have another window that will come through, and this will go on from here. But a business use case for this might be every 10 seconds, give me the count of new tweets. So now we have no overlap between our windows. It's important to note that if our slide interval is greater than the window size, then we might be dropping data on the floor. Let's say that our slide interval is 20 seconds and our window size is only 10 seconds. Then we'll evaluate every 20 seconds only 10 seconds worth of data. So as we choose these parameters, it's important that we understand these concepts and choose them very, very carefully. The next set of semantics that we'll review very quickly are stream processing semantics. There's at least once processing, which means that if I restart my data pipeline for any sort of failures that happen within my data system, then there might be duplicates that arrive in my data stream. And for some scenarios, this might be okay. For a connected car, vehicle, telemetry platform, if we have some duplicates, that is still tolerable. If you imagine a financial transaction model, this will not work. As financial transactions, we cannot have any duplicates. Next is at most processing. This says that we will allow duplicates, but we can restart the system and still have a couple of data that come through after the time. Finally, we have exactly once processing. And this is very, very hard to achieve, but this is where we see a lot of enterprise customers really want their streaming pipelines to be capable of. And we won't walk through the internals of each one, but what is important to note is we'll walk through which technologies offer which stream processing semantics so that when you have to choose these technologies, you can understand with what latencies do they provide these semantics and which ones provide these capabilities. So before we evaluate these technologies, I'm going to make a distinction here, and this is more of a model distinction. The ones denoted in orange are open source technologies for streaming. The ones denoted up top, which are namely Azure Event Hubs and Azure Stream Analytics, are multi-tenant services that are offered on Azure. And when we evaluate these technologies, it's important that we understand these models because it's not a full apples-to-apples comparison. So let's start with Event Hubs and Kafka first. If you look at HDInsight Kafka versus Azure Event Hubs, this table shows that they're pretty comparable technologies. I'm not going to go through every single row of this table, but for the most part, if you're just getting up started and running, they're both going to achieve the same thing, and they offer the similar capabilities. Similarly, for Azure Stream Analytics versus Spark Streaming or Storm on HDInsight, they again offer similar capabilities. They're both capable of doing windowing semantics. They're both capable of doing exactly once processing. So what do we need to pay attention at? So the first thing we need to pay attention for is performance and scalability. Because of their multi-tenant natures, Azure Event Hubs and Azure Streaming Analytics have certain throttling limits in place per subscription for you. You can, of course, call Microsoft to get these limits increased, but if you look at the HDInsight model that we will drill into a little bit, you get a cluster, which means that if you have any performance or scalability issues that you hit, you can just scale the cluster up and add more nodes, and you pay as you go. Next is your developer ecosystem. If you have a .NET-friendly shop, if you have a SQL-friendly shop, you might not want to spend developer cycles making your developers understand open source technologies such as Java, Scala, Python. That being said, there's a lot of work being done in the open source community to have parity with SQL and with C#. For example, Spark offers Spark SQL. We've done a lot of work to do C# with Storm. But if you have an open source friendly developer ecosystem, then you might want to deploy open source technologies. Next is developer support. So let's say you deploy all these technologies in your production pipeline. Now, if you run into any issues with the open source technologies, those technologies have been out there for a while. They're deployed at many, many enterprises. If you run into any issues, you can quickly do a Stack Overflow search. You can quickly do an Apache form search, and you might get the answer back within seconds. Versus if you run into any problems with Event Hubs or with Azure Stream Analytics, if it's not a published sort of bug, or if it's not a known issue, then you might have to call Microsoft support. You might have some lag time for your developer support there. And then finally, there's ease of use. So while HDInsight minimizes the cluster overhead that you have to manage your cluster, there's still, at the end of the day, a cluster that you get that you have to manage. Versus Azure Event Hubs and streaming analytics are just endpoints on Azure. It's just a pick up and go model. There is no cluster management involved. So given these sort of trade-offs, you want to understand which technologies fit in best for your use case and make a call between the open source on HDInsight versus the multi-tenant models. And that's not to say that they don't interact with each other. You can have event hubs that interact with Storm, or you can have Kafka that interact with other analytics as well. So for the rest of this session, we will focus on HDInsight. HDInsight empowers you to deploy open source technologies on Azure. Open source technologies such as Kafka, Storm, and Spark Streaming have been out there in the industry for quite some time. And as this slide shows, they have been deployed at many, many companies. In fact, a lot of these technologies were born out of these companies. Kafka was born at LinkedIn, where they claim that you can process trillion events per second. Storm was developed at a company that was acquired by Twitter, and then there were a lot of developments that went through on Storm. They did a lot of the trending now through Storm, fraudulent tweet detection through Storm. And then Spark is the newest darling of big data. It is deployed at every single big company that we can think of: Uber, Microsoft, Netflix, Amazon, and so forth, right? And you can check more on which companies are using which technologies, but this is just scratching the surface. So open source must be great and really easy to use, right? Since a lot of these enterprises are using them. Does everyone agree that open source would be easy to set up, administer, install, and use? All right. So in reality, open source, while it is great, there are a lot of challenges with working with open source. The first one is, it's very hard to set up, install, administer, configure. Not only do you have to go ahead and purchase the hardware, if you have it on premises, you also have to identify which cloud am I going to pick, which machines do I need to deploy. Then you have to have the in-house talent that knows these technologies in and out so that they can go ahead and install and tune these technologies for your business use case. Then you have a scaling problem. Let's say that you want to add more and more nodes. You have to understand how these technologies work so that you don't disrupt the existing pipeline. Open source is also not very secure or does not offer compliance features. So if you have a financial company, or if you have medical records that you're processing, you have certain compliance needs that you have to meet. Open source does not offer these compliance, and with compliance, not only do you have to do it once, every so quarter or every so often, as according to your company policy, you have to go ahead and implement compliance. So it adds to a huge total cost of ownership for deploying open source. You might have different support models for open source, such as if you go ahead and deploy a Cloudera instance or a MapR one, you have to go first find which cloud am I going to deploy on, and then you have to deploy these bits. Now, if you have this pipeline up and running, that's great. But let's say something fails in this pipeline. First, you have to identify, did it fail at the VM level, or did it fail at the end-to-end bits level? Then you have to contact that specific company. You have to go through that model. It's a very clunky sort of support model. And finally, there's a huge cost to operationalize and monitor these open source technologies. Your big data pipeline always has to be up and running. In the case of streaming scenarios, it has to be running 24/7, which means that you have to have a team in place that's constantly monitoring this pipeline. If a node goes down and your system is deemed unstable, you're dropping data on the floor, which cannot happen for a big data pipeline. So again, this adds to your huge cost to own and operate open source. That's where Azure HDInsight comes into play. And how many of us are familiar with Azure HDInsight? There's about 4 people. How many of us have deployed a cluster on Azure HDInsight? 1 person. Great. So Azure HDInsight is fully managed cloud Hadoop and Spark. And I'll go through what that means. But we offer more than just cloud Spark and Hadoop. We offer 99.9% SLA on the full uptime of your end-to-end solution. So this is not just the VM instances. This is not just the bits. It's on the full solution of your Hadoop workloads. It is fully open source. We partner with the Hortonworks data platform, so you get the full open source bits. And every single addition that we do, we make sure that it is open source compliant. In addition to this, any sort of customer features that we get to have in HDInsight, we ensure that they go back out into the open source Hortonworks distribution. We also offer enterprise-level monitoring and support through Azure Operations Management Suite. And I believe there was a talk on OMS a couple of days ago. But the key differentiator for OMS is that not only does it give you the capability to alert and monitor your data pipelines, it also provides you automation runbooks against these metrics. And we've done a lot of work in HDInsight, as we'll see, to expose out these metrics so that you can take predictive actions against your cluster's health so that you don't have to monitor it 24/7. And in addition to this, we've done a lot of work, as we'll explore with Spark, to ensure that you have a great developer experience if you're working with open source on HDInsight. We have a lot of developers' tools that plug into your IntelliJ IDEs or your Visual Studios to ensure that you have full experience from a developer standpoint for open source technologies. In addition to this, we are a service that's built on top of Azure. So not only can you reap the compliance benefits that Azure has to provide, HDInsight does a lot of work to make sure that the bits that are deployed are HIPAA compliant, they're PCI and SOC compliant, so that you can upload your medical data into the cloud and run computations on it. And the Hadoop space is now very, very complex with the leading ISVs. You can do a lot more with ISV providers such as StreamSets, Cask, Datamere. We provide a very, very rich native experience that we'll walk through on how you would go ahead and deploy these versus you going ahead and then getting one of these ISVs, figuring out how would that integrate, how would the licensing model work, and go from there. So HDInsight offers, these are the workloads. It offered 5 up until this year. There was Apache HBase, Hive, Spark, Apache Storm, our server, and as of this year, we've added Apache Kafka to the HDInsight family. And we've not just added HDInsight Kafka as a random workload, but as we can see, there's a missing puzzle piece for deploying an open source streaming pipeline on HDInsight, which is namely the stream buffering technology. And that is where Kafka completes the open source streaming solution on Azure HDInsight. Not only does Kafka complete this picture, we've done a lot of work, as we said, with Operations Management Suite to ensure that we expose out the native JMX metrics for each one of these workloads. And we're doing a lot of work to ensure that the full end-to-end streaming pipeline is built for enterprise use case. And there's a talk on Azure HDInsight for enterprise later today, which I would also encourage you to attend, by Erica. So while we have this, why don't we walk through a quick demo of how easy it is to set up this pipeline on HDInsight? Because traditionally, this used to take enterprises months to get up and running. So if I am to just walk to my Azure portal, this is the Azure portal. We can go and click on plus. And if we go to Intelligence and Analytics, HDInsight should be the first one that pops up into the Azure Marketplace. We click on HDInsight. I can just give it a cluster name. And this is the cluster UI. And we also offer ARM templates, which I'll go through in a bit, to automate all of this deployment. But as you can see, we offer all of the Hadoop workloads, and there are others in preview, such as Kafka. We offer both Linux and Windows. And so once you hit select, you can then go ahead and through the portal, you can show all the administrative actions that you can take, which is you can provide a cluster login password, a secure shell password, and so forth. Let me just give it. Doesn't seem to like my password. All right. And it seems like internet here is a little bit slow, but we can also configure meta stores. So if you want to have transient clusters that spin up and down, you want to save your Metastore information somewhere so that you don't have to recreate that from scratch. So we offer a Hive Metastore service as well, which you can configure. Or you can bring in your own SQL database. And finally, we give you a summary on how many worker nodes you have, and this is the simplified UI. If you go to the customizable UI, you can choose how many worker nodes you want so that you can really scale the cluster up and down. And HDInsight does offer this elastic model where you can scale the cluster up and down, and we'll see why that is important in a little bit. So if we go back to this slide here, the way you would deploy the streaming pipeline is you would deploy a Kafka cluster and you would deploy a Storm cluster, and these would all be within the same Azure Virtual Network. And then since they're in the same Azure Virtual Network, they can communicate with each other without having to pay a performance penalty. To make this deployment even simpler, if you just go to our website for the documentation, you can say deploy to Azure, which brings you to a template. And it seems like apologies here, the page reloaded on me. So in this template, it's a really nice UI where you can give all the parameters, but not only can you give all the parameters, you can go ahead and change all of the resources that you want to deploy, and we offer a very nice JSON sort of ARM template here. And in the parameters, you can say which type of clusters you want. So in this case, we'll be deploying a Kafka and a Storm cluster within the same VNet. And once we do deploy this out, it will take 20 minutes, and you have a streaming group where we take care of deploying all of the network gateways, the clusters, and your VNet settings. And we'll come back to a working example of this in a bit. This is really powerful, as this would take enterprises a long time to get up and running. And we've gotten a lot of enterprise customers asking us, why do we separate out the clusters? If, for example, they deploy Kafka and Storm within the same cluster, and why would they have to go on HDInsight and deploy two separate workloads for this? And in general, in cloud computing technologies, we want to decouple technologies as much as possible. Kafka, since it's an event buffering technology, it is an I/O-heavy technology, which means that it does not need a lot of CPU power, but your disks will start to get very, very full. Versus Storm, on the other hand, is a compute-heavy technology. You need to have some sort of, you need to have really beefy machines to process all the events that are coming in. So if we have these in the same cluster, then what might happen is, because of scaling needs, let's say your Kafka starts to be the bottleneck, and now your disks are starting to get really, really filled. So now you have to scale the cluster up and add beefy machines that have both disks and CPUs, while your CPU just sits idle because you have a disk problem. Or if you take the other scenario, where you have compute needs for Storm, but Kafka is really not the bottleneck, you'll be adding more and more nodes that have high disk usage, but the disk will just sit idle. So if we decouple the two, you can scale each of these independently, and you can really have some cost savings by providing cheaper VMs for your Kafka and having really beefy VMs for Storm. As your workloads increase, you can scale the Storm cluster up. As they go down, you can just scale the cluster down to really save on some costs. All right, we just talked about this. So before we can do a comparison of both Storm and Spark Streaming and Kafka, let's walk through a little bit a deep dive on what is Kafka, as it is a very new technology. So Kafka is a high throughput, low latency messaging service. It was developed at LinkedIn, like we just mentioned before. It is a simple publish and subscribe model. It is highly resilient, which means that it is very, very suited for cloud architectures. And it scales linearly as throughput increases. What I mean by this is, if you have your scaling needs, that if you have to scale your cluster up, you don't have to pay a performance penalty with Kafka for a giant cluster. So let's walk through an example to really understand how Kafka works. So if you deploy a Kafka cluster on Azure HDInsight, in this example, we have a 3-node cluster, and a node would be analogous to a broker. And Kafka also has a dependency on this technology known as Apache Zookeeper. Apache Zookeeper, in a nutshell, is a technology where it is built for concurrent, resilient, and low latency transactions. So a lot of technologies such as Hadoop workloads do a lot of state management through Apache Zookeeper. So we walk through a simple example where we have one producer sending data to one topic, which is a logical grouping of how Kafka manages information. It will send information to one topic, which in this case has one partition, and one consumer will then consume from that same topic. In this case, life is good. However, let's say we have additional consumers that enter into our example. And this consumer doesn't have to be a process. It can be an additional core that is sitting on your box. Since Kafka is an offset-based technology, the additional consumers cannot take advantage of the fact that cannot consume from the same partition. So to mediate this problem, Kafka offers partitions. So if we go ahead and recreate our topic with the appropriate number of partitions as our consumers, then we can see that we increase our throughput, and Kafka is a highly parallelizable technology. Now, in this case, we have parallelism that is great, but in cloud architectures, as we know, things can always go wrong. So let's say that we have a broker failure. A node goes down. Now, in this case, our system is deemed unstable because not all the partitions are available, and we don't have full completion of our data. To mediate this problem, Kafka offers replication factors as well, and it does a lot of smart placement of your replicas for each partition. So it will replicate each partition and elect a leader, denoted by the L in this diagram, for each partition. And it will place them smartly so that in the case of a broker failure, so in this case, it had partitions 2's leader replica on node 2. Kafka will recognize that this leader is down. It will go ahead and query all the other brokers to understand where is another replica for partition 2. So in this case, there is broker ID 3. Kafka will then go ahead and elect that as the leader. It will then go ahead and store this information in Apache Zookeeper and route all your producer traffic to partition 2, to broker ID 3, and also route all your consumer traffic to partition 2's new leader. So now we've walked through how resilient and parallelizable Kafka is. This is a very naive example with one topic. As you can see, you can have multiple topics and multiple consumer groups consuming from a Kafka cluster. And as your storage needs increase, you can just scale the cluster up. So go ahead. I'm sorry? It does not create a new replica. It will, so the question was, does it create a new replica as well? So Kafka will not create a new replica. It will wait until the node comes back up, and it will go from there. So Kafka is great, but why might you want to use Kafka on Azure HDInsight? So as we mentioned before, Kafka has integration with native integration with Azure Operations Management Suite support. This is important for Kafka because if we go back to our example where we have the Kafka clusters and it's a disk-based technology, let's say that in your cluster, your disks are 80% full. You have an alert that says my disks are 80% full. But now we can have a customized run action against our metrics. And since HDInsight offers this scale-up functionality, we can say if my disks are 80% full, please add an additional node to my Kafka cluster. So it's really important that we have this native operations management suite support. Kafka as a technology was developed for other cloud environments, not specifically to Azure. So they deployed rack awareness. However, rack awareness, the way they had deployed it was through a single dimensional unit. Azure, on the other hand, has this concept of an update domain and a fault domain. Update domain is the set of machines that will be updated at any given point in time when you roll out an update. And a fault domain is a set of machines that is attached to a single pod. So if there's network connection that is broken to that pod, then all of the machines in that pod will fail. So it's known as a fault domain because it acts as a single point of failure. But because of this two-dimensional matrix, we had to do a lot of work in Kafka to make sure that whenever you push out updates, that your updates are UD aware and fault domain aware. And we have a replica rebalance tool that goes ahead and smartly rebalances your replicas as you scale the cluster up and as you push out updates. And we've also open sourced this tool for Azure environments. And there are other environments that use this concept as well. HDInsight is the only platform in the industry to provide a managed Kafka. When we were talking with a lot of customers for their Storm or Spark deployments, they were using Kafka on-premise or Kafka on their own. And they had a lot of trouble managing Kafka, installing it, making sure that it's always up and running. Because of this, we deployed Kafka, and we see a lot of customers come to HDInsight because they're interested in Kafka and they're interested in the SLA that Kafka provides. Additionally, in the example that we had just walked through where there is a broker failure, Kafka reacts to this, this is still within a single data center. So while Kafka can process single data center failures, we might have a full data center that might go down. And this is really important for large enterprises, especially for their disaster recovery scenario. So Kafka offers this technology known as Mirror Maker, and we offer support for Mirror Maker that allows you to do cross data center support for disaster recovery scenarios. Right, so those were most of the Kafka highlights. Now let's talk about the stream processing engines, namely Storm and Spark Streaming. And we'll do a brief walkthrough of them and then go through the differences between them so that you can make the key trade-offs when you have to choose these technologies. So let's start with Apache Storm. So an Apache Storm is an event-by-event processing technology. The Apache Storm has this idea of a tuple, where a tuple is just a key value pair. In this case, it's going to be an event. A sequence of unbounded tuples is known as a stream. And streams feed into a spout. And the spout is a source of streams, and it wraps a streaming data source. This is the spout API. There's a lifecycle API to open, close, activate, deactivate. This is the core API, which is the next tuple. It will just give you the next tuple in the stream. And this is the reliability API, which will be important for achieving the stream semantics for at least once, at most once, and exactly once that we had talked about. Storm also has this concept of bolts. And bolts really provide you the extensibility to do custom logic that is tailored to your business needs within Storm. You can write data to store using a bolt. You can read data from store. You can perform some computations on your data. This can be averages, group bys, sums. And you can emit another stream. So it's really important to understand that bolts can take in a stream and also output a stream, which means that you can hook together a lot of the bolts to have a lot of these complex topologies that we'll see in a minute. And this is a very simple bolt API. It has a lifecycle API, and it has the core API, which is execute. And this is where you would go ahead and plug in all your code that you need to do any sort of logic, any sort of transformation that you have with Storm. So if you combine spouts and bolts, we have the concept of a topology. In this case, we have two spouts that go to different bolts that will then emit another stream, which will go to another bolt. And as you can see, you can put all these bolts together to really have a tailored experience for your enterprise use case. So let's walk through an example of how you would architect the topology. So let's say that you wanted to understand all the tweets that are coming in. What languages are they coming in? What is the count of languages? So we'll have a Twitter spout, which will then send a stream of data to a bolt where you can say, I'm just going to do a count of all the languages of the tweets that's coming in. And maybe I'll write that to a store that is going to go to a dashboard. So Storm is very powerful. We can do this in 4 lines of code with Java code in Storm. And Storm also has this concept of a trident. Trident is an extension of Apache Storm. And as they said, it is built for stateful stream processing and low latency querying. The main idea of Trident is that it is a fluent stream-oriented API that provides you a high-level abstraction to perform all the necessary computations such as averages, group bys, sums. So you don't need to go ahead and implement all of that code. Trident will do that for you. Trident, it's important to know that Trident uses microbatching, and we'll go and understand what microbatching is and why that is important when you have to make a decision. And Trident is how you would achieve exactly one semantics with Storm. Without Trident, we cannot achieve exactly one semantics with Storm. So while Storm is great, why is it better on HDInsight? Again, as similar case as Kafka, we're the only platform to provide Storm as a managed service with a 99.9% SLA. We also have, similar to Kafka, native operation management suite support with Storm, where we expose out all the metrics, which really allow you to scale your cluster up and down as your needs grow. But the key differentiator for Storm and HDInsight is that when we talk to a lot of customers, they said that they use C#, but they really want to leverage the power of Storm. However, they did not want to spend development cycles learning Java or training or putting that infrastructure in place. So Microsoft developed this technology known as scp.net, where you can write your Storm topology in C# within Visual Studio, and then submit that to a Linux cluster that is running Storm. And we will do all of the work behind the scenes to translate your C# code into something that will be a Storm topology. And this is Microsoft developed, and this is one of the key differentiators for using Storm on HDInsight. Finally, let's talk about Apache Spark. And as we can see, Apache Spark is the newest, hottest technology in big data. And this is a very famous diagram that is pulled straight from the Spark website. But Spark is a platform. It is not just used for streaming. You can use Spark for Spark SQL. You can use Spark for streaming. You can do machine learning through Spark. You can do batch analytics. So Spark has tremendous, tremendous opportunity in front of it. I won't go into all the details of Spark. Just to give you context, last Ignite, I think there were 3 sessions on Spark alone. So Spark is a very, very vast area. However, let's go through some of the key takeaways of Spark. As I said before, you can do big data tasks from one platform, which is data cleaning, ETL, streaming, machine learning, and interactive queries within one platform. This is really important for that Lambda architecture that we had talked before, because it really reduces your overhead for working with one technology versus working with either Storm for your streaming and then Hive for your ETL and then something else for your interactive. Storm is extremely fast. It is built with in-memory constructs such as resilient distributed data sets known as RDDs, or data frames, which is available in Spark 2.0 plus. Spark is also very easy to use. They provide a rich notebook experience for your data scientists, where from one browser window, you can do everything from streaming data to cleaning the data to running some machine learning on it to providing some results through it. It also has Scala, Java, and Python support, which really provides for a nice developer experience. You can do machine learning from within 4 lines of code of Scala. So why is Spark better on Azure HDInsight? Again, it's a fully managed service. We did a lot of work in this last release of Spark to ensure that it is HIPAA compliant and PCI compliant. We had a lot of customers that wanted to upload health data, so we ensured that we provide the open source compliance for Spark on Azure HDInsight. There's also a lot of work done to provide a rich notebook experience for your data scientists and data analysts. So previous to HDInsight, if you had a notebook that was running, and let's say for some reason your browser would crash, you would lose the state of your notebook, and you'd have to go ahead and redo all the work that you'd done through the notebook. So HDInsight developed state management on notebook experience. So now if your notebook crashes, if you want to close the browser, no worries. You can go ahead and restart your notebook, and it will pick up from the last checkpoint where it had started. In addition to this, we make sure that Spark is very, very nicely integrated within the whole Azure data ecosystem. So we have seamless integration with Azure Data Factory to construct your ETL pipelines using Spark on HDInsight. We also have Power BI connectors for both Spark streaming and for Spark as your batch processing unit. So it really provides for a nice technology to use for your Lambda architecture. So we can keep talking about Spark for a while, but for the purposes of this session, I'm going to focus on Spark streaming. So Spark streaming comes in 2 different flavors. The first one is known as direct streaming, or DStreams. And the second one, which was released last winter as of Spark 2.0, is structured streaming. And while I won't go into the details of what each one of these are, we'll go through the trade-offs between the 2 very, very quickly. So DStreams had some limitations when it had first come out. Out of order processing of events was not handled very nicely in DStreams. There was also exactly once processing was not guaranteed with the DStreams APIs. There was also not a single unified API between your batch analytics and your streaming analytics, and checkpointing was not implemented very efficiently with DStreams. However, in the new set of streamings, they do guarantee exactly once semantics using Spark streaming, and they guarantee they do provide support for windowing semantics that we had just talked about, and they unify the streaming APIs to be compatible with your batch APIs and your interactive APIs. So now you have your static and your continuous data going through a single API. So if we just walk through an example of this, if your batch ETL pipeline looks like input equals spark.read and output equals spark.write, then your streaming one, you can just change from spark.read to spark.read stream and output write to write stream. And on the internals, it works the same way as it does for batch versus streaming. And as we can see, it really provides a nice use case with that unified API for both the batch and the speed layer if you have to use a Lambda architecture for your data needs. Spark also provides great support for continuous aggregations, group bys, and it also provides these windowing aggregates that we were talking about before, where you can do sliding windows or tumbling windows within Spark. So, one last thing is Spark does fit in really nicely with the open source ecosystem as well. They have really native APIs for doing data ingestion through Kafka, joining a static data set. So this is where the Lambda architecture always comes in place, is you can join a static data set for the streaming APIs, and then you can write that back out to a joined data set into your streaming pipeline as well. So while we talked about Spark and Spark streaming, there's one important caveat that we did not mention with Spark streaming, which is namely micro-batching. So if we look at the speed layer and the batch layer, there's a small intersection between the two, which is known as micro-batching. And to illustrate what micro-batching is, I think it's going to be helpful if you just walk through an example. So if you go back to our tumbling window example, where we had data coming in continuously for each windows, if we just zoom into that first window of 0 to 10 seconds, and if we were to just take, let's say, 5 as our event, with micro-batching, 5 is actually not an event. 5 is a logical grouping, and if we were to zoom into 5, in Spark's case, 5 is a micro-batch labeled as 5. It is a set of RDDs that it is going to say is a batch that I'm going to process as a single unit. And that set of RDDs has a batch interval associated with it. So now your window interval will be a function of the batch interval, and your slide interval will also be a function of the batch interval. So this is important to note, as this adds processing latency for your streaming jobs. That being said, it also provides for higher throughput. So we really want to do an analysis of what are the latencies that we're going to live with for our streaming pipelines, and what are the throughput needs of our streaming pipelines to understand if micro-batching is something that we want to enable. And if you go back to Storm's example, if you remember, Trident uses micro-batching as well, and the only way to achieve exactly one semantics using Storm is also using micro-batching. So we cannot get around this micro-batching problem, but we need to do an evaluation of do we want event-by-event processing, or do we want micro-batching? So to sum up, if we were to just compare and contrast Spark streaming and Storm, Spark streaming supports micro-batching only for all streaming scenarios. This adds to latency, but might lead to higher throughput. Storm, on the other hand, does event-by-event processing for everything but exactly once. If you have to do exactly once, we'll have to do micro-batching as well. Spark provides lower overhead for Lambda architectures. It has a single unified API, so it has lower overhead if you were to deploy this out and use this for your pipelines. And again, Storm has Trident. With Trident, if we were to do a comparison of performance between Spark streaming and Storm, then there are no published benchmarks. There's no, it wouldn't be an apples-to-apples comparison. You would really have to look at your use case and then understand where the latencies are, which ones are you willing to live with, and go from there. So in general, both support windowing, both support transformations, both support exactly once. You want to understand your scale needs, your developer ecosystem. Do you want a simplified API for batch and streaming, or do you want different technologies for each one of these architectures? So let's walk through an example of Spark and the notebook experience with Kafka. So you remember, we had deployed a Kafka cluster with Spark. And if I just go to the homepage of that, okay, I think this will take a little bit of time to load, but Once it does load, I'll show you how to get to the notebook from the Spark portal. But once we get to the Spark UI, this is what a Spark UI looks like. If we just click on this notebook, it is a IPython notebook, and we will just walk through this notebook to show how we can stream data from Kafka into Spark within a single browser window. It is a simple example for a streaming use case. So first, we're going to create a Kafka topic. In this case, I named my topic Ignite AU03. So I'm just going to go ahead and create that topic. And it says created topic Ignite A03. We will SSH into our Kafka cluster to see this data come through as well. Then this notebook walks you through all the necessary steps involved in getting this pipeline up and running. We're going to configure our streaming package. We're going to import the necessary classes that we have for getting this application up and running. We're going to create a Spark application that is going to be our streaming application. We're going to submit the Kafka configurations, and we're just going to do a simple word count example. I have just 5 sentences here that I'm going to send 1,000 messages for Kafka to. I'll create a streaming context. And this is what is going to be deployed on the Spark's end that is going to wait for the events, that is going to pull the events from Kafka and perform the streaming actions. So let's send our messages to Kafka. And if we go to our Kafka cluster, this should show all of the messages come through to our Kafka. As we see, we sent 1,000 messages to Kafka. They came through. And now, since I have streaming context already deployed on my Spark, this code, what it does is it goes through, gets the streams of the sentences, it puts them into a map, does a word count, and then stores the result back out to a SQL table. So if I just go ahead and view the word counts, I can say select star from word count. And as we see, the word counts examples come through in our Spark notebook. So in one single browser window, I was able to stream data to Kafka, or stream data from Kafka, perform the word counts on it, and then display the results back into my browser window. This really shows the power of Spark streaming and the power of Spark as a technology. In addition to this, let me go back to the cluster dashboard. So if you were to go to our Kafka cluster, the Kafka UI exposes out a Ambari UI, which Ambari is a open source cluster service manager that we have heavily integrated HDInsight with. You can stop and start services through here. You can monitor your brokers and all the information through here. But if you look, it also exposes out your Zookeeper information. So what I did for the IoT scenario that we had before was I could just go ahead and join my laptop to the VNet that I had created, get the Zookeeper IP addresses, and then use an arbitrary open source technology. This one is called Node-RED. And this is how I had created the connected car scenario that we had seen before. And all I had to do was point a Kafka node, which this has support for, and give it my Zookeeper IP addresses. This would then go ahead and automatically configure Kafka, and as we saw before, it goes through and does that connected car dashboard. So this really shows you the power of running open source and how easy it is to get up and running. You have support with other third-party tools, and they integrate very, very nicely with open source. All right. Finally, let's talk about our customers. So one of our customers is Bing Shared Data. Their code name at Microsoft is also known as Siphon. But they power the full data bus for Microsoft. All telemetry flows through them for Windows 10, for Exchange, for Office 365. And they process about 4 petabytes of data per day. They have 6 million events per second that they're processing, and this is all done through Kafka. And the reason why they had moved over from their on-premise devices to Kafka in the cloud was because they had enormous amounts of cost for implementing compliance. Since we are a service, again, built on top of Azure, they got the compliance for free, so they migrated onto Kafka on HDInsight, and this is the amount of load that they're processing. This is their key customer scenario, and their scenario was that within about a few seconds to a minute, Office 365 has a lot of click-through rates that come through. They want to do some real-time insights into how customers are using that service and provide some real-time telemetry and some real-time machine learning to surface out different content on the web page depending upon how users are using their service. So that was the kind of use case for one of the customers that Siphon has. This is their architecture on how they're deploying Kafka and their streaming pipeline. As you can see, they have built out a REST interface in front of Kafka, and they've deployed out Kafka with other technologies in each of their data centers. This is where disaster recovery scenarios really come in handy for our enterprises. In addition to this, Bing Ads had this requirement where they wanted to guarantee data completeness before they kick off any more transactions. So they went ahead and built out an audit trail where they go ahead and run Kafka to Spark streaming. From there, they do an Elasticsearch search, and this will come back to guarantee 99.98% completeness. And this is one of the features that we see a lot of enterprises also wanting to implement as data completeness, how much data from this data pipeline has been processed from my streaming job. So they are a customer that is using one of our services, HDInsight, at petabyte scale as well. And this goes through a more in-depth analysis of how the brokers are set up with the REST API. As you can see, the REST is in front of a public load balancer. Data will flow in, and it will route it to the appropriate data collectors, which will then route it to Kafka. So with that, I'll open up with questions. That's all. Yeah, go ahead.
This architecture supports like querying, real-time display, etc.
Yeah.
Is there any built-in support for alerting?
For HDInsight?
Yeah, in this like, I've just processed my data, got some conclusions, I want to just send an email, send a tweet, whatever.
Sure.
Does it do alerting out of the box? Or do you have
So you can configure a Spark application to do alerting. There's a lot of APIs that have that as well. But you can use Operations Management Suite to do all the alerting. It can send emails. It can raise ICM tickets. If you have a infrastructure in place to raise tickets every time your service goes down, it can do that as well. But yeah, there's alerting, monitoring, and then also predictive actions built in through OMS. So you can write it. I'm sorry?
OMS will integrate into this?
OMS will integrate into that slide that we had before. If I zoom back in. So everyone, actually, before I close this out, please remember to take your evaluations. I believe there, if you take your evaluations, you get some prize for Adventure Sports tonight. So make sure you complete your evaluations. So OMS would fit into this, where you would have your Spark application, and it will then, let's say, put out a metric. I completed X job. You can then configure an OMS run action or an alert to say, send an email.
Oh, okay.
Yes. Go ahead. Is there any plan for Stream Analytics to consume Kafka? So we are looking at it. There is no shareable date yet, but we are looking at that. Any other questions? Go ahead.
So with this data factory, at the moment to create a Spark job, you have to, from my experience, you can only do that through a MapReduce activity type.
Mm-hmm.
And so you have to create a jar file, load that up, and have all your data there. Is there any plan to make it like you can have, say,
Yeah.
an R1, so just kind of like how they've got the Hive activity,
Mm-hmm.
but then the R activity you can run within Spark or
I see.
the configuration is easier.
So the question is there any support for other cluster types, not just Spark, to configure that activity from data?
So in Data Factory, when you want to run Spark, you have to use a MapReduce job and supply a jar file.
Yes.
Is there any way, is that going to be simplified in the future?
I see.
That you could just say supply some SQL and use a Spark SQL Data Factory activity?
I see. So none that I know of so far, but if that is a pain point, then we can talk offline and see how your use case might be simplified. There might be better ways to do what you have to achieve there. Go ahead. Any other questions?
Yeah.
One in the back.
Yeah, can you use on-premise to, if you've got your own sort of streaming stuff, just sort of like your laptop?
Yep. So like sort of this case where I have, where the data is streaming to my laptop and then it goes to that. Yeah, so what I had done was I had deployed all of the Kafka and the Storm in a VNet. And then we have documentation, and we also have ARM templates for how you would deploy a VPN client. And what this will do is, so what I had done before the demo was I'd installed the VPN client onto my laptop. And this is the VPN client that you would get. Let me see. It doesn't have to. And it doesn't have to limit the I/O connection. You can still go through the max network throughput. I think it's like 10 Gbps. And then if you have different, you don't have to deploy everything out into the same VNet as well. We have documentation on how you would deploy this out into one VNet. And then you can deploy other resources into other VNets. And then you can use VNet peering to peer the VNets together and then set up a custom DNS so that all the information will resolve and the data will flow through.
And could you use like your own Azure, they have an Azure dedicated link service?
Your own Azure Data Link service?
Yeah, well there's a customized link service to do data ingestion. Could you use that or you have to use the VPN type arrangement?
No, you can use different types as well. In this case, I used VPN, but there are different ways to configure your on-premise connections to talk to the Azure VNets. You can also lock those down using network security groups, and there are third-party appliances such as Barracuda Networks that you can lock these down as well.
So you can pretty much use any sort of gateway
Yes.
connection?
Yes, that is correct. You can use any sort of gateway connection. Anything that works with Azure VNet currently will work with this whole streaming pipeline. And we do have customers that have this hybrid story where they have a lot of streaming data that streams onto their on-premises devices, and they don't want to upload all of that to the cloud, maybe for confidentiality reasons, or they just want to keep that data secure. So they'll scrub it, and then they'll just send some of the data back up to the cloud. So that hybrid story is definitely supported.
Yeah, I mean, could you do like gigabyte a second stuff?
Could you do?
Gigabyte a second? Sort
Yeah,
of?
you could definitely do gigabytes a second. You should be able to get gigabytes a second. Yep. Any other questions? Great. Thank you, everyone, for attending. Yeah. Again, remember to fill out the evals. Thanks.